Hello, calculus students and seekers of truth. In this video, I am going to explain this one particular problem using polar functions, mostly determining where this polar graph has a tangent line and where it has a horizontal tangent line and where it has a vertical tangent line. And then you'll see just a heads up, as you see me walk through this video, you're going to see lots of algebra and trigonometry, and that's actually going to dominate most of the video content. But I don't want you to lose track of the greater meaning of all of this stuff, all of this work, which is kind of the calculus concepts. Okay, so lots of messy details, but a very clean and simple overarching conceptual understanding. Is what we're aiming for here. All right, so let's get to it. So I have a polar function. R is expressed in terms of theta equals 1 plus sine of theta. And we want to find where the graph has a horizontal tangent line. And so a horizontal tangent line, right, that suggests is where dy dx is equal to 0. And over here, a vertical tangent line is where dy dx is undefined. So that's big picture. Now what we also want to know is, well, we got a function here in terms of r and theta, and how are we supposed to express this in terms of x and y? Well, if you recall, dy dx is going to be equal to dy d theta divided by dx d theta. It's not because of the fraction, it's actually because we're using the theta variable here as sort of like a parametric or a parameter in the set of parametric equations. And so this is going to be an important detail that we work with. This is dy dx. That's going to be equal to dy d theta over dx d theta. But now, how do we convert from theta and r into terms of y and theta? And so here I'm going to remind you of another important detail, and that is that I'll write it right here, that x is equal to r cosine theta, and y is equal to r sine theta. And so this is intrinsic to the property of polar functions to go back and forth between polar and rectangular. This is the conversion that we're going to use. Okay, so remember, dy dx is equal to dy d theta over dx d theta, and x and y are actually related this way. So we got a lot of variables going on here and quite a few derivatives. So it's important we keep that in mind. Okay, so with that in mind, let's get on with the work here. I'm going to clean up my screen a little bit, and then we will proceed further. All right, so specific to our problem, x then is equal to r, which is 1 plus sine theta times cosine theta. And y is equal to the same thing, r sine theta. So 1 plus sine theta, sine theta. And then I'm going to work through the details here. Dx d theta, that's the derivative of x relative to theta, is going to be equal to negative sine of theta. I'm sorry, let me backtrack just a little bit. Sorry about that. I'm just gonna distribute this cosine and the sine throughout. So this is x is equal to cosine theta plus sine theta cosine theta. And y is going to be equal to sine theta plus sine theta, or sine squared theta. Okay, so just distributing that. I'm going to change colors here when I go to take the derivative. So dx d theta is going to be equal to the derivative of this statement up here. So that's going to be negative sine theta, and then we got to use the product rule. So derivative of sine times cosine is cosine times cosine, which is cosine squared, plus the derivative of cosine, which is negative sine times sine. You get negative sine squared theta. So that's dx d theta. dy d theta will be equal to cosine theta plus 2 sine theta cosine theta. And so now this is probably the extent of the calculus concepts here. We got everything pretty much figured out. And now we got to go and just do a lot of algebra and trigonometry. Okay. So now, if we know that if we're looking for a horizontal tangent line, that means dy dx has to be equal to 0. I'm going to rewrite this back in here. Remember that dy dx is equal to dy d theta over dx d theta. Okay. So if the numerator is going to be equal to 0, then the whole thing is going to be equal to 0. So to check for the horizontal tangent line, we're going to check to see where dy d theta is equal to 0. And so that's what I'm going to do here. So check for a horizontal tangent line, we're going to check where dy d theta equals 0. So that tells us that 0 is equal to cosine of theta plus 2 sine of theta cosine of theta. All right, and at this point, we get into some algebra and trigonometry. So I want to solve this equation. On the right side, I can factor out a cosine theta, and that leaves me with 1 plus 2 sine theta. The zero product property applies here, so I can split it into 0 equals cosine theta and 0 equals 1 plus 2 sine theta. Cosine is equal to 0 at pi over 2 and 3 pi over 2. Over here, you're going to end up with negative 1/2 is equal to sine of theta. Know your unit circle. Theta will be equal to 7 pi over 6 and 11 pi over 6. And more, right? There's infinitely many answers for theta that we can plug in here. We just keep adding periods onto each of these points, right? So this is where in pre-calc you're going to add like 2 pi n, where n is an integer, to each of these points in order to get infinitely many. Now, I want to point out here that the answer that we're looking for is not going to be in terms of theta, it's going to be in terms of x and y. Okay, so we don't need to worry about infinitely many points because once we look at the graph, it's just going to cycle through repeatedly. And I'll show you what the graph looks like kind of at the end of all of this. Okay, so now I want to back up and say we have values of theta and we want find all points, right? Find all points. So points here, we're still in the rectangular world, points x, y. So we're going to take theta and plug it into this equation and get an x value. And then we're going to take theta and plug it into this equation down here and get ourselves a y value. And that's exactly what I'm going to do. All right, so from here on out, we're working a lot here with the unit circle. So I'm just gonna make a couple columns here in my table. The first thing is gonna be theta, and then it's gonna be the x value, and then it's going to be the y value. Okay, let me give myself some more space here because I think some of these expressions are gonna take a little bit of time to write. Okay. All right, and I'm gonna go through this quite quick because I rely on you to review and practice working with the unit circle and simplifying. But I am going to show you what the final answer is, of course. So the first thing here, when theta is equal to pi over 2, So that means I plug plot pi over 2 into here, right? Now, when theta is equal to pi over 2, x is going to be equal to cosine of pi over 2, which is 0. So that's just going to wipe the whole thing out. So that's easy enough. And then when theta is equal to pi over 2, I'm going to have 1 plus the sine of pi over 2, which is 1. 1 plus 1 is 2. Sine of pi over 2 is also 1. So that's going to give me a grand total of 2. So one of my points where you have a horizontal tangent is going to be 0, 2. All right. When I try 3 pi over 2, putting into here, I'm going to get the same thing, right? So cosine of 3 pi over 2 is 0. So that's also going to give me 0 for x. And same thing down here. I'm going to have, or almost same thing down here. Sine of 3 pi over 2 is going to be -1. So adding it to 1, that's going to give me 0. So 0, 0. Now I'm going to put an asterisk on this because we're going to return to this. This is a kind of a tricky thing. We're going to deal with it towards the end here. So I promise I'm going to go back. Okay. Let's do another one. How about at 7 pi over 6? At 7 pi over 6, sine of 7 pi over 6 is -1 plus 1. That's, sorry, -1 half plus 1. That's going to give me 1 half. 1 half times cosine of 7 pi over 6, which is -√3 over 2. So all in total for the x, I'm going to get -√3 over 4. And then for the y values, again, 1 plus -1 half is going to be 1 half. Sine of 7 pi over 6 is -1 half. So that's going to give me -1/4. Okay. For the last point, I think I'm running a little bit out of space here. Okay. So let's see if I can squeeze this in here a little bit down here. So for 11 pi over 6, same thing, sine of 11 pi over 6 is going to be -1 half plus 1, that's 1 half. Cosine of 11 pi over 6 is going to be √3 over 2. So when we multiply that out, we're going to get positive √3 over 4. And then here, we're going to get positive 1 half times -1 half. So that's going to give me -1/4. So these are the 4 points. Well, 3, this second point here is going to be a little bit tricky. Okay. So hopefully that helps you a little bit, gives you a better understanding of how we got to this point. Again, there are infinitely many answers, right? It's pi over 2, 3 pi over 2, 5 pi over 2, 7 pi over 2, and so on. But none of that really matters because all those extra points don't really matter, because if I were to plug 5 pi over 2 into this equation, I would get these same points. So we're looking for specific xy points, xy coordinates on this polar graph. All right, now let's move on to the vertical tangents. Now, back here, we have a vertical tangent line. That means dy dx is undefined. And since dy dx is equal to dy d theta over dx d theta, that means if we're dividing by 0, if dx d theta is equal to 0, then dy dx will be undefined. And so that's exactly what we're going to check here. Now, we already figured out what dx d theta is. It's this lengthy thing right here. And so we're going to set that whole thing equal to 0. Negative sine theta plus cosine squared theta minus sine squared theta. Okay, now this equation is going to be a little bit more challenging for us to solve. just because we got some mixtures of x's and y's and squares and non-squares in there. So let's go slow. So from what you understand, and hopefully what you maybe remember a little bit from trigonometry pre-calculus, is when you have a mix of sine and cosine and you can't separate them like we did over here, then one thing you could do is try to convert them. And this is what I'm going to convert. I'm going to convert this cosine squared. Remember this old, comfortable, nice and good Pythagorean identity that cosine squared plus sine squared equals 1. Therefore, cosine squared on its own must be equal to 1 minus sine squared. It must be. So this part right here, cosine squared, I'm going to convert that into 1 minus sine squared theta. And then I'm going to finish out the rest of this problem. 0 equals negative sine theta plus 1 minus sine squared minus another sine squared. Let's combine this. Let's simplify or combine our like terms here. So I get 0, and I'm going to rearrange things a little bit, is equal to 1 minus sine theta minus 2 sine squared theta. And then you see here, we actually have nothing more than a quadratic where sine of theta is the variable. So we can factor that like we would most quadratics. This is going to factor into 1 plus sine theta. Hopefully there's lots of nice, good memories coming back in from pre-calculus and trigonometry. I always love this part where you have something that seems trigonometric in nature, but then you realize, oh, it's just a quadratic. Okay, so if you were to take this and distribute everything, you would return back to the statement right here. So that means these two statements are equivalent and they're equally true. And so now let's see, what can I do here? Well, I can split them again, right? So I can say 0 is equal to 1 plus sine theta, and 0 is equal to 1 minus 2 sine theta. Solving each of these equations, I get that negative 1 is equal to sine theta, and that means theta is equal to 3 pi over 2. And over here, 1/2 is equal to sine theta, and that means theta is equal to pi over 6 and 5 pi over 6. And then we're going to continue on. Let's make our table just like we did before. And remember that this is the conversion from theta into x and y. All right, so if we were to plug 3 pi over 2 in for theta, we would get negative 1 for sine. So this would wipe everything out and we would get 0. Same thing down here. For the y value, sine of 3 pi over 2 is negative 1 plus 1 is 0. That would wipe out. And you see now why I put the asterisk over here. So at 0, 0, the graph both has a horizontal tangent and a vertical tangent, which can't be true. Okay? You can't have both. What you end up with is you're going to have dy dx is equal to 0 over 0, which is an indeterminate form. And once we work all that out with L'Hopital's rule, we'll see that it's actually a vertical tangent line. So we're going to cross this off right here because this isn't true. I'm going to spare you the details of L'Hopital's rule for right now, and I'm just going to show you what this graph looks like when it's all said and done. Okay? Now let's do pi over 6. Okay, so let's go quick here. Sine of pi over 6 is equal to 1/2. 1 plus 1/2 is 3/2 times cosine of pi over 6, which is root 3 over 2. So you're going to have 3/2 times root 3 over 2, which is going to be 3 root 3 over 4. Down here, same thing. You're going to have 3/2 times sine of pi over 6, which is 1/2. So 3/2 times 1/2 is 3/4. And then now for 5 pi over 6. Well, Still the same, the sine of 5 pi over 6 and the sine of pi over 6 is going to be the same. So you're going to have 3 halves times negative root 3 over 2. So that's going to be 3 root 3 over 4. And then for y, when you plug in 5 pi over 6 into theta, you're going to get negative 3/4. Okay, so the points here that I've written in red, that's where you're going to have a horizontal tangent. And the points that I've written here in purple, there's 3 of them, that's where you're going to have a vertical tangent. And then I think just to bring home this idea, I am going to show you a nice looking graph of this to just really let all of the concepts gel together. All right, so here we go. Here's a pretty nice looking graph of the whole thing. This is I've graphed here using our favorite tool in Desmos. We got the equation right here. That's the green graph. It kind of looks like an apple. The technical name for this is a limacone curve. Um, when we have, you see the points here, 0, 2, there's 3 orange points, 0, 2, and you see what I plotted over here. See, that's where you're going to have a horizontal tangent line, and then the 3 purple points, the one on the left, the one on the right, you're going to have vertical tangent lines. And this one right here at 0, 0, remember according to the algebraic work, it was where it was going to be both horizontal and vertical. That can't be true. It's just vertical. And you see, if I zoom in on here, I get the green curves get ever more steeper. Okay, so that tells me, or that at least confirms, that it's going to be a horizontal tangent line. So there you have it. Hopefully, this example, I know it's tough, it's a little bit tedious, it draws on lots of interesting ideas from pre-calculus as well, but it gives you a better sense of how to approach these questions with derivatives, tangent lines on a polar graph. As always, thank you for watching and have a wonderful day.